Hi, this is Stephanie Eckman, and I'm going to present today my paper, Precision of Estimates in Non-Response Bias in Means. This is joint work that I've done with my RTI colleagues, Jennifer Unangst and Jill Deaver, and also with Chris Antoun at the University of Maryland. And the idea for this paper came out of a session at the Joint Statistical Meetings in 2015 in Seattle. Chris was presenting his dissertation work and Jill was a discussant. I was in the audience, Brady was there, Mike Elliott and Mike Brick were there as far as I remember. And there's really a really interesting discussion about sampling variability in non-response bias estimates. So out of all that work came this paper. And I want to say thank you and also to Kristen Olson and Sung-Hee Lee. This paper has been under review at the JSAM journal, AAPOR's journal, and Kristen is the editor there, Sung-Hee is the associate editor, and their comments have really improved this paper. So as I said, this paper deals with non-response bias estimates, particularly in means. And a lot of surveys are now publishing non-response bias estimates where they can, where they have the data to do so. And of course, OMB requires estimates of non-response bias in surveys for many federal surveys as well. And so I started thinking about how do we use these estimates of non-response bias? Well, certainly one use, and probably the most common, is to judge the quality of a particular survey. So if you're interested in using data from the current population survey in March of 2018, you'd want to know how much non-response bias is there in that survey, in certain estimates from that survey, as a marker of, is this a good quality survey? Is it going to be appropriate for the purposes that I want to use? But another reason we would use non-response bias estimates is to predict or understand how much non-response bias will there be in future surveys. So you might look at the current population survey in March of 2018 and the patterns of non-response bias there as a way to think about how much non-response bias is there going to be in the 2019 March current population survey or the 2020 March current population survey. And when we're making inference from one survey, of course, to another, I think we need to worry about these estimates of sampling variability. So for example, you might do round one of a survey and show that you have low response from households in the Northwest. So we have some bias in the percent of households from the Northwest in round one of the survey. What are we going to do with that information? Are we going to change our protocol for round two of the survey, maybe the next year, by offering higher incentives or using a different field strategy in the Northwest to try to reduce that non-response bias? And it isn't straightforward exactly what you're going to do with an estimate from round one and what that means for round two. And that's what this paper is focused on. It could be that non-response bias exists in round one because of the sample that we selected. Maybe we got unlucky and got a weird sample of people in the Northwest with different characteristics. And if we were to repeat round one or do round two of that same survey, we would get a different sample and we get a very different pattern of non-response bias. And so we need to worry about sampling variability in our non-response bias estimates. We know this, of course, when we're talking about other estimates of means from surveys. We know that each estimate of a mean from a survey has a confidence interval around it. And we need to account for that sampling variability in estimates, but we very rarely do this when it comes to estimates of non-response bias, which are essentially really also sample estimates of a population value. And they should also have these confidence intervals or standard errors that capture sampling variability. So this paper looks at two things: how variable are non-response bias estimates across samples from the same population, and then how do we estimate the variance or the standard errors on these non-response bias estimates. So as I said earlier, I've got, with the four of us here, we have a full paper on this, and I can't get into the whole thing. The paper is available on Open Science Frameworks for anyone who wants more information. So we use a simulation study to address these two questions. And as you can see here on the screen, let me get my pointer. We've got Y, which is our variable of interest. This might be household income or age that you first used marijuana, right? And then we've got this variable Z, which drives the response propensity. This is related to how likely people are to respond to a survey. And these two variables are multivariate, normally distributed. And understanding the nuts and bolts of this isn't really important. I just want you to draw your attention to these two parameters. There's delta here, which controls the response rate. And we looked at two different response rates, 30% and 70%. Sort of a low response rate and a high response rate. I know some surveys would love to get 30%. It's not always considered a low response rate in all modes, but those are the values we've chosen here in the simulations. And then there's rho, which is the correlation between Y and Z, or the correlation between what we're measuring, what we're interested in, Y, and how likely people are to respond. And so this rho characteristic, this rho parameter, drives how much non-response bias there is in the survey. And sometimes rho is 0 and there is no non-response bias, and sometimes it's higher, about 10%, leads to about 10% non-response bias. So we can manipulate these parameters and look at how they affect those two research questions, how variable the non-response bias estimates across samples are, and how do we estimate the non-response bias, the variability of that non-response bias. We also looked at a third parameter, which is phi here, which controls the clustering. So are the clusters in the population homogeneous? That would be a phi of 0, or are they variable, which would be a different setup. So again, here is the full setup with all three of the parameters shown. We generated populations for each different set of combinations of phi, delta, and rho. From each population, we selected 2,000 samples of size 1,000. And sometimes we selected simple random samples, and sometimes we selected multi-stage clustered samples, because of course we see both of those designs used in different surveys. From those Z's, we could build these response propensities, which run from 0 to 100 and represent how likely each case is to respond. We did that in two different ways. We first did deterministic response, so that each case in the population is flagged as always a respondent or always a non-respondent. No matter how many times it gets sampled, if it's sampled in 100 of these 2,000 samples, every single time it's going to respond or not respond. Alternatively, we could do, stochastic response, right? Where each case decides to respond or not respond every time it's sampled. So if a given case is in 100 of the 2,000 samples that we selected, some of the times it responds and sometimes it doesn't respond. Both deterministic and stochastic response are driven by this response propensity. So turning to our two research questions, the first is, how variable are these non-response bias estimates across samples? So here we see the sampling distribution for these non-response bias estimates for a given population setup. So the population setup here has a response rate of 70%. The samples are unclustered, and there's no bias in the population. That rho parameter is 0. There's no correlation between Y, the variable we're interested in, and Z, which controls those response propensities. So what do we see here? The height of this curve is sort of like how common those those values are. So we see that most of the 2,000 samples here are centered right around 0. The non-response bias estimate is 0. Most of these samples are, when we estimate non-response bias from the sample, the answer is 0 or right around 0. However, there are some weird samples out here where we're getting estimates of like -2% or 4% or 5%, right? There are some weird, some bad samples that are out here and give us answers that are quite far from the population value of non-response bias, which is 0. However, one of the things we also see in this graph is that there's very little difference between whether we use the deterministic method of assigning response, non-response, or the stochastic method. These two curves are basically right on top of each other. I personally found that result rather surprising. When we look at a different population setup here, we have a lower response rate from 70% to 30%, and we are now doing a clustered sample rather than a simple random sample. And we see that this distribution is shorter and thicker. And what that means is we have fewer samples that are estimating near 0. 0 is still the true amount of bias in the population, but fewer samples are estimating right around 0. And we've got more of these bad samples that are giving us like -5, -7, or +5, +8, right? So this thicker, shorter distribution means that the estimates of non-response bias are more variable when we have a lower response rate and a clustered sample. Now, this is just two populations. We, in fact, ran many more. Here is a summary of 8 of the different populations that we ran. So here we're not showing that whole normal curve. We're just showing sort of the endpoints, the 2.5% to the 97.5% range. This column represents all the populations where the response rate is 30%. This column is all the populations where the response rate is 70%. And then we've got no clustering in this top row and clustered populations in the bottom row. And we see here that clustering is making these distributions slightly wider. So this one here is slightly wider than this one up here, but really what's driving it is the response rate. So these low response rates are really widening those distributions and making our estimates of non-response bias less precise. What this means is that when you have a low response rate and you estimate non-response bias for a sample, that estimate of non-response bias is not necessarily a good predictor of the true non-response bias in the population or non-response bias that you would get if you were to redo that survey. Moving to our second research question, how do we estimate the variance of non-response bias estimates? We compare 3 different methods in the paper: the Lee method, the replication method, and the linearization method. So the Lee method, this comes from Sung-hee's paper in 2006, where she starts with this formula, may look familiar to most of you. The non-response bias is equal to the product of 1 minus the response rate and the difference between the respondent and the non-respondent means. She takes the variance of this by pulling out this 1 minus response rate term, squaring it, and then in square brackets here, she's got the variance of y bar r plus the variance of y bar nr. For those of you who are familiar with how the variance operations work, there is a missing term here, which is -2 times the covariance of the y bar r and the y bar nr. That is not in this formula, essentially assuming that it's 0. There are some other assumptions built into this formula that we get into in the paper. But Sung-hee uses this formula in her paper to estimate the variability of non-response bias estimates. So this is one of the methods that we evaluate. The others are replication and linearization. I'm not going to talk about how we did those. We give an algorithm in the paper for those of you who are interested. So in this slide, we see the coverage rate of 95% confidence intervals. So a 95% confidence interval should have 95% coverage, meaning that in 95% of the samples, those confidence intervals include the true value. And we've got 95% here indicated with these solid black vertical lines. So if these confidence intervals are performing as expected, the symbols in the graphs should cluster right around that vertical line at 95%. And that is mostly what we see, except down here in this graph, where the Lee method is producing confidence intervals that have much greater coverage. This means that the standard errors and the variances and the confidence intervals built around that Lee method are much too wide. And so we're going to fail to reject the null hypothesis that there is no non-response bias, when in fact we should reject. This means we're going to have like not enough statistically significant findings because our confidence intervals are incorrectly too large. So then that was all from simulation data. And then the editors encouraged us to look at real data as well. And so we looked at the LISS survey, which comes out of the Netherlands, is an unclustered web survey, and at the General Social Survey, which is a clustered survey in the US. And the outcome we're looking at here is the ratio of the standard error calculated from that Lee method and the standard error calculated from the replication method. If these 2 methods are producing similar standard errors, this ratio should be 1, right? And that's what we see when we look at the LISS data. So we looked at these 6 variables in the LISS data, and the vertical line here is right at 1, and we see that that ratio of the Lee to the replication standard error is right around 1. The 2 methods are producing similar estimates of standard errors. However, when we look at the GSS, we see that it differs a lot by variable. So one of our variables has a ratio near 1, but as we go down the graph here, we see that the ratio is increasing, and down here by own gun, the ratio, the standard error from the Lee method is more than 6 times larger than the standard error from the replication method. And that's because the General Social Survey is a clustered sample. That's the same result we saw from the simulation, but it is nice to see it here in the real world results as well. So the takeaways here are that the estimates of non-response bias in means do vary across samples, and we should recognize when we're reporting non-response bias for a given survey that it is just one estimate from that distribution of all the possible non-response bias estimates. We need to be careful when we're generalizing from one sample to another. If you select one sample and get non-response bias, it may not necessarily tell you much about what you would get if you were to repeat that sample. The Lee method does work well for unclustered samples. The Lee method is also easier to calculate, which we go through in the paper. So that's a nice choice if you have unclustered samples. Replication and linearization work best with clustered samples, and we do give an algorithm for how to do those in the paper. These results also hold for binary and count variables. That is in the paper. I didn't have time to explain it today. Thank you very much. You can find the code and the paper here on Open Science Framework, and I'm happy to answer any additional questions about this work. Thank you.